Greetings everyone, this is Professor Roman. Let's continue the lecture series on linear algebra. We've seen examples of operator modules that have non-trivial annihilators, and we've seen operator modules that have trivial annihilators. Let's suppose that v sub tau has a non-trivial annihilator. Then among all the non-zero polynomials that annihilate v tau, we can select one of smallest degree. And then we can, if necessary, multiply this polynomial by the inverse of its leading coefficient in order to produce a monic polynomial of smallest degree that annihilates v tau. And temporarily I'll denote that by m of x. This polynomial is very special. If p of x is any annihilator of v tau, we can divide p of x by m of x, get a quotient and a remainder. The degree of the remainder is less than the degree of m of x. But for any vector, little v in v tau, p of x v is 0. That's equal to q of x m of x v plus r of x v. M of x v is also 0, so that's just r of x v, which tells us that the polynomial r of x annihilates every vector. But as I said, its degree is less than the degree of m of x, and the only way that does not result in a contradiction to the minimal degree of m of x is if r of x is 0. And that means that p of x is a polynomial multiple of m of x. In other words, every annihilator is a polynomial multiple of m of x, or put a different way that is often said, m of x divides every annihilator of the module. So the annihilator of v tau is the consists of exactly the polynomial multiples of m of x. In addition, m of x is unique because if m1 of x is also a monic polynomial of smallest degree that annihilates v tau, then each of m of x and m1 of x would divide the other. But they're monic and they have the same degree, so they're equal. That's precisely why we require the property of being monic to make the polynomial unique. Well, all this calls for an important definition. Let v tau be an operator module with non-trivial annihilator. The minimal polynomial of tau, also called the minimal polynomial of the operator module, v tau, is the unique polynomial m tau of x of smallest degree that annihilates the operator module, or put another way, that is satisfied by tau. And we'll use three different notations for this minimal polynomial. It depends on the context. Sometimes one notation seems a little better than another. M tau of x when we need the variable so we can make substitutions, min tau or min v tau. Most authors, I think, most courses in linear algebra, if they discuss the minimal polynomial, will refer to it simply as the minimal polynomial of tau and not of v sub tau. But it's convenient to do so, and it doesn't matter. We have the vector space v, so tau uniquely defines v tau, and v tau uniquely defines tau, so it doesn't really matter. This is the summary let v tau be an operator module over a field F with non-trivial annihilator. Then tau has a minimal polynomial. And the annihilator of v tau are the multiples, polynomial multiples of the minimal polynomial. Oftentimes, this is read, or it's stated this way. If p of tau is 0, then the minimal polynomial divides p of x. This is sort of the operational version. This is what we use most of the time. Well, we've seen that not all operator modules have non-trivial annihilators. If the module has a trivial annihilator, it doesn't have a minimal polynomial. But all finite dimensional operator modules, which are the ones we're mostly interested in, have non-trivial annihilators, and therefore they have a minimal polynomial, or more specifically, tau has a minimal polynomial. And to prove this, all we need to do is show that there's a non-zero polynomial p of x satisfied by tau. But if the dimension of v is n, then the dimension of the vector space of linear operators on v is n squared. We talked about that some time ago. And so this list of operators, the identity tau, tau squared up to tau to the n squared, there are n plus 1 of the n squared plus 1 of these, but the dimension is only n squared, so they must be linearly dependent. Here we see the importance of the fact that L of v tau is also a vector space. So there are scalars in the base field, not all 0, for which this non-trivial linear combination equals 0, or put another way, this polynomial is satisfied by tau, and so annihilates v tau. All finite dimensional operator modules have non-trivial annihilator and therefore, in particular, have a minimal polynomial. Just a little tidbit here that may be useful. If S tau is a submodule of V tau, then the minimal polynomial of the restriction, tau restricted to S, will be denoted by this same type of notation. But for readability's sake, if you look here at this one, I dropped the sub tau on S because 3 levels of subscripts is kind of difficult to cope with. Had to do it here, but the less I have to do it, the easier it is to read, I think. You should convince yourself that if v tau has a non-trivial annihilator, so does any submodule of v tau. If a finite dimensional operator module, v tau, has a minimal polynomial, in other words, if its annihilator is non-trivial, and if b is an ordered basis for v, then we know that p of tau is 0 if and only if p tau sub b, the matrix representation of p tau, is 0, but that's the same as p of the matrix representation of tau. This is something you should convince yourself of. Also has to do with the nice behavior of the matrix representation map. Therefore, the polynomials that are satisfied by tau are the same as the polynomials that are satisfied by the matrix representation of tau. Any matrix representation. B was an arbitrary ordered basis. In other words, the annihilators are the same, and therefore the minimal polynomials are the same. So the minimal polynomial of tau is the same as the minimal polynomial of any matrix representation of tau. In terms of similarity classes, all the matrices in the similarity class these are the matrices that represent tau under different order bases, they all have the same minimal polynomial. It's the same as the minimal polynomial of tau. That means the minimal polynomial is yet another similarity invariant. We've seen that the characteristic polynomial is as well. Unfortunately, the minimal polynomial is, again, not a complete invariant. So here is the official statement. V tau is a finite dimensional operator module. The minimal polynomial of tau is the same as the minimal polynomial of any matrix representation of tau. The minimal polynomial of a matrix is a similarity invariant. Similar matrices have the same minimal polynomial. That's easy enough to prove directly. Now we can say that every linear operator tau on a finite dimensional vector space has associated with it two extremely important polynomials, the characteristic polynomial and the minimal polynomial. Both of these polynomials provide significant insight into the nature of the operator. Characteristic polynomial, for example, tells you about the eigenvalues. We'll also see later in this chapter that there's a strong relationship between the two polynomials. There's a very famous theorem called the Cayley-Hamilton theorem, and it says that the minimal polynomial divides the characteristic polynomial. That tells us, among other things, that the roots of the minimal polynomial are also roots of the characteristic polynomial, and therefore eigenvalues if they lie in the base field. But more can be said beyond that, and that is the root sets over the base field of both polynomials are the same. And so that's the spectrum of the operator, the F spectrum. F is the base field. The best we can say concerning multiplicity is that the multiplicity of a root of the minimal polynomial is less than or equal to the corresponding multiplicity for the characteristic polynomial. And most of the time it will be less. When we discussed the characteristic polynomial, we discussed the relationship between the characteristic polynomial of a restriction of the operator to an invariant subspace and the full characteristic polynomial. We should do the same for minimal polynomials. And we do it in matrix language because it's simpler and it tells us everything about the operator language as well. Here is a block upper triangular matrix. If the asterisk represents only 0 entries, then this is also block diagonal, so it covers both cases. The nature of block form matrix arithmetic implies that if P of x is a polynomial, then P of A has this form. You take P of the blocks on the diagonal. This stuff up here will change, but if this asterisk represented only 0 entries. In other words, if this was block diagonal, this will be also block diagonal. These will be all zeros. Well, if P of A is 0, if P annihilates the operator module, or if just A satisfies the polynomial P of X, then each of these must be 0. P of BK must be 0 for all K. The minimal polynomial of A, remember A is a matrix as well as an operator. The minimal polynomial of A is satisfied by A, and so the minimal polynomial of A is satisfied by all these small blocks, diagonal blocks. So the minimal polynomial of each block, these are smaller matrices, but they're still operators on an appropriate space. They divide the minimal polynomial of A. And since all of these divide MA, the least common multiple, which I'm calling Q of X for want of a better notation, it divides the minimal polynomial of A. For characteristic polynomials, there was an equality. The characteristic polynomial was A is the product of characteristic polynomials of the diagonal blocks. Here we can't quite get that sharp result. The least common multiple of these minimal polynomials divides the minimal polynomial of A. But if the original matrix was block diagonal, we can do better, because Q of X, this least common multiple, is a multiple of every one of these minimal polynomials. So Q of BK is 0 for all K, and therefore Q of A is 0. And so the minimal polynomial of A divides Q of X. That's the opposite divisibility property here. And therefore we have equality. The minimal polynomial of A is equal to the least common multiple of the minimal polynomials of the blocks on the diagonal. Again, for the characteristic polynomial, this was the characteristic polynomial of A is equal to the product of the characteristic polynomials. So we have a sharp result, equality, but this one's a little more involved, I guess you might say. From an operator perspective, suppose tau is a linear operator on V, and that S tau is a submodule. In other words, a tau invariant subspace. What we can do is extend an ordered basis for the submodule to an ordered basis for V, and this is what the matrix representation will look like. We've discussed this before. So the minimal polynomial of the restriction of tau to S divides the minimal polynomial of tau. If we have a reduction of tau, then we're going to have block diagonal matrix, and so the minimal polynomial of tau is the least common multiple of these minimal polynomials. Here's a summary of everything we've said, and for contrast, in comparison, I added the characteristic polynomial. Oh, that comes later, sorry. This is just a summary of what we've done. V is a finite dimensional vector space. From a matrix point of view, A is up. Let's let A be an block upper triangular matrix. The minimal polynomial of each block divides the minimal polynomial of A, and so the least common multiple will also divide A. But this is probably somewhat more useful. Just one generally deals with each block separately, so I have this. But if A is block diagonal, then the minimal polynomial is equal to the least common multiple. In particular, and this is something that will come up, so I wanted to mention it explicitly, if the minimal polynomials of these blocks are pairwise relatively prime, then the minimal polynomial of A is the product of the minimal polynomials of the blocks. This will come up because what we will do in the future, and this is key to getting at the structure of a linear operator, is to take the minimal polynomial and factor it into prime powers, prime power factorization, just as you could do with an integer. And the prime powers, distinct prime powers, are pairwise relatively prime. This is the operator perspective, which I just went over, so I won't read it again. This matrix we talked about earlier, and we have a direct sum decomposition. This is an ordered basis V1 through V8 that produced this matrix. We have this, I'll write, just to simplify the notation, write tau sub k instead of tau restricted to S sub k. This is a reduction of tau. You can tell from all the zero blocks that that this direct sum is a reduction of tau. Each of these subspaces is tau invariant. This is the characteristic polynomial. It's the product of the characteristic polynomials of each block. It comes out to be this. The minimal polynomial, because the matrix is block diagonal and not just block upper triangular, is the least common multiple of these three minimal polynomials. Now the minimal polynomial of tau 1, tau sub 1, the restriction of tau to S1, is just the minimal polynomial of this block. How do we find these minimal polynomials, and therefore the minimal polynomial of tau? Well, the Cayley-Hamilton theorem would be of considerable help here, but we're not entitled to use that theorem because we haven't proved it yet. I haven't even stated it officially. In this case, fortunately, it's not too difficult to get the minimal polynomials directly, because I kind of cheated and I made these blocks relatively simple. In particular, this is lower triangular. So, and the diagonal elements are all the same. So if I take b minus 2i, I get something strictly lower triangular. And as you raise that to powers, you will hit 0, always. And so what we know here is that b satisfies this polynomial x minus 2 quantity cubed, which means that the minimal polynomial is a divisor of this, but it's not x minus 2 or x minus 2 quantity squared, because they're non-zero when you substitute for b, substitute b for x. And so this is, in fact, the minimal polynomial. And you can do similar arguments for the other blocks. And so the minimal polynomial is the least common multiple, seem to have an extra comma there, least common multiple of these three minimal polynomials, and that's equal to this amount. Okay. And if you compare that to the this is quantity x minus 2 cubed, x minus 3 cubed. If you compare that to the characteristic polynomial, x minus 2 to the fifth, x minus 3 cubed, you can see that, am I getting both of these here? You can see that the minimal polynomial divides the characteristic polynomial, but the multiplicities here of 2 and 3 are less than or equal to the multiplicities here, and in fact 2 has smaller multiplicity in the minimal polynomial than it does in the characteristic polynomial, but the root sets are the same, 2 and 3. Now I have a summary. I might want to make this into a theorem, I'm not sure. Doesn't really matter. For matrices, as far as the characteristic polynomial is concerned, these are the two matrices we're looking at. Block, diagonal, block, upper triangular. I split them here. This case covers this case, but it's a little nicer, I guess, if I split these. Okay. The characteristic polynomials of both of these matrices are equal to the product of the characteristic polynomials of the block matrices. The minimal polynomial for this matrix is the least common multiple of the minimal polynomials of the diagonal blocks. In this case, the best we can say is that the least common multiple of the diagonal blocks divides the minimal polynomial. Okay? So the characteristic polynomial situation is simpler. Doesn't matter which you have, block diagonal or block upper triangular. The characteristic polynomial ignores everything off the block diagonal. You just take the product of the characteristic polynomials of the block diagonal blocks. Yeah. Minimal polynomial is more complicated. In this case, the minimal polynomial is the least common multiple of these minimal polynomials. In this case, the least common multiple simply divides the minimal polynomial of A2. So we don't really know what the minimal polynomial is here exactly. There are operator versions of this, and we've already discussed them, so I should go over them just to be clear. We have a linear operator tau, and suppose it is reduced by a direct sum. So each of the subspaces is tau invariant. This is the better case. This is what we're striving for. Then the characteristic polynomial of the operator is the product of the characteristic polynomials of the restricted operators. And the minimal polynomial is the least common multiple of the minimal polynomials. If all we have is a single tau invariant subspace or submodule, then what we can say is the characteristic polynomial of the restricted operator divides the full characteristic polynomial. Same thing for the minimal polynomial. We've already seen that the characteristic polynomial of a matrix is field independent in the sense that the coefficients of the characteristic polynomial lie in the smallest field that contains the entries of the matrix, regardless of which field we take to be the base field of the matrix. So, for example, if we have a matrix with only rational entries, generally we would think of that as a real matrix, but the characteristic polynomial will have rational coefficients. An identical statement applies to the minimal polynomial. And to prove this, we're going to use the field independence of linear independence, something we discussed in Chapter 1. So you might, if you have the book, you might want to go back to Theorem 1.82 and review that. It's an unusual theorem I haven't seen elsewhere. It's not terribly complicated, but it's needed at this point. Here is the theorem in particular that we need. Let f and k be fields, and let k be an extension of f. If S is a set of matrices, m by n matrices over the smaller field f, then if this set is linearly independent over f, it's also linearly independent over the bigger field k. It's conceivable that if you have more scalars available, you might be able to find a non-trivial linear combination that's equal to 0. And this is saying you can't. Okay, now suppose that we have an n by n matrix over the field f, and k is an extension of f. And we'll denote the minimal polynomials of A as a matrix over f and over k using the superscript f and superscript k. Now, the f minimal polynomial is also a polynomial in k squared bracket x because k contains f. And the f minimal polynomial is satisfied by A, and therefore by definition of the k minimal polynomial, it will divide the f minimal polynomial. So that's half the battle, the somewhat easier half. We're trying to show these are the same. Well, if the degree of the f minimal polynomial is d, then these matrices, these D matrices, are linearly independent over f. Because if there was a dependency, you would have a polynomial, non-zero polynomial of smaller degree than D that was satisfied by A. We're talking about over f now. Okay, these matrices we're thinking of as belonging to the matrices over f. So that's when we apply this theorem, this one here, that says, therefore, that these matrices are also linearly independent over k. And so the k minimal polynomial has degree at least d, but it divides the F minimal polynomial, which has degree D. So the two polynomials have the same degree, and since they're monic, they're equal. So let A be a matrix over F, then the minimal polynomial and the characteristic polynomial of A have coefficients belonging to the smallest field that contains the entries of A. And so they are both base field independent. One additional fact about minimal polynomials before we start actually using them. A theorem back in chapter 4 said that for any field F containing the entries of A, so we could think of F as a base field, the roots of the characteristic polynomial that lie in F are precisely the eigenvalues of A that lie in F. The F spectrum is the F root set of the characteristic polynomial. This also holds for the minimal polynomial. The F root set of the minimal polynomial is the F spectrum. As to proof, suppose first that lambda is an eigenvalue of A, belongs to the spectrum. It belongs to the F spectrum of A. So AV equals lambda V for some non-zero eigenvector V in Fn. But we know that A satisfies its own minimal polynomial, and so the spectral mapping theorem, which we discussed in chapter 4, tells us that 0 equals M sub A of A, that's the zero matrix, that zero matrix times V, and this is the spectral mapping theorem. It says this is equal to this. Well, if this product is 0, this is a scalar multiple of V, and V is non-zero, the scalar must be 0. So any eigenvalue in the F spectrum is a root of the minimal polynomial. For the converse, suppose that we have a root of the minimal polynomial that lies in F. Then call it R. Then x minus R is a factor of the minimal polynomial over F. And so we can factor out x minus R, divide by x minus R, get another polynomial which I called m sub tau of x. Its degree is less than the degree of ma of x, less by 1. So m tau is not satisfied by A. It's got degree smaller than the minimal polynomial of A. So m tau of A is non-zero. This is a non-zero matrix, so there has to be a vector for which this product, which I call W, is non-zero. But when you apply A minus R to W, it restores this thing we factored out, and we get back to the minimal polynomial, whose, when you apply that to V, you get 0. And so W is an eigenvector for A with eigenvalue R. So every root r of the minimal polynomial is an eigenvalue. So we can now state, this is something I showed you earlier that we would eventually show is true. A is an n by n matrix over F. The two polynomials have the same set of roots in F, and the roots are precisely the eigenvalues in F, the F spectrum. But the multiplicities don't have to be the same. I suppose it might be worth mentioning that this does not quite prove the Cayley-Hamilton theorem. It tells us the root sets are the same, but it doesn't tell us that the multiplicities of the roots with respect to the minimal polynomial are always less than or equal to those with respect to the characteristic polynomial, which is what we would have to have in order to say that the minimal polynomial divides the characteristic polynomial. Cayley-Hamilton theorem is one of the cornerstone theorems. It's going to take a little more work to prove, and we'll do so at the end of this chapter. So we've got a bit of ground, a fair amount of ground to cover before we can give an elegant proof of the Cayley-Hamilton theorem. The minimal polynomial of an operator provides a characterization of diagonalizability of operators. We've already discussed diagonalizability, and it was back in chapter 4, and the presence of the minimal polynomial will give us one more characterization. So just to review, this is the theorem from chapter 4. Phrased in terms of operator modules. Let v tau be an n-dimensional operator module, and let the spectrum of tau be lambda 1 through lambda m. Then the following are equivalent. Tau is diagonalizable. Remember, that means that it can be represented by a diagonal matrix. The pair v tau, or equivalently the operator module v sub tau, has an eigenbasis. That's a basis consisting of eigenvectors. And in that case, then the matrix representation of tau with respect to that eigenbasis is a diagonal matrix, and I've used this notation to save space here. So this is a matrix that is diagonal. We'll have some copies of lambda 1 followed by some copies of lambda 2 and so on the main diagonal. In fact, each eigenvalue is repeated as many times as its geometric multiplicity specifies. V is the direct sum of the eigenspaces of tau. The sum of the geometric multiplicities is equal to the dimension of the space. The characteristic polynomial, and now we know also this will apply to the minimal polynomial, splits over F. And all of the eigenvalues are non-defective, meaning that their geometric and algebraic multiplicities are the same. That's where we concluded the theorem in chapter 4, but now we can add one more item. The minimal polynomial of tau splits into a product of distinct linear factors. So all we need to do is prove that this last condition is equivalent to any of the others. If tau is diagonalizable, then we know that the operator module is a direct sum of eigenspaces. Lambda 1 through lambda m are the distinct eigenvalues. Therefore, this polynomial which we hope we're trying to show is the minimal polynomial, does annihilate each eigenspace. X minus lambda 1 annihilates the eigenspace associated with lambda 1 and so on. So this will annihilate all of the operator module, which means that the minimal polynomial of tau will divide this polynomial. So it has only linear factors. The question is, does it have all of these linear factors? Well, if a proper factor of p of x annihilated v tau, we can assume by reindexing that it's just x minus lambda 1 quantity multiplied by the quantity x minus lambda m minus 1. So from lambda 1 to lambda m minus 1, that this annihilates the operator module, because if some proper factor of this annihilated the module, then a proper factor missing only one of these factors would annihilate also, and we can assume that missing factor is lambda m. But now we have a problem. This polynomial q of x and x minus lambda m are relatively prime, and they both annihilate the last eigenspace E sub lambda m. X minus lambda m annihilates this, and q annihilates everything. But we had a theorem earlier in this chapter that if two relatively prime polynomials annihilate a vector space, then that space, or a subspace, then that subspace is trivial. And so we would deduce from this that E lambda m is trivial, which is ridiculous. Eigenspaces have eigenvectors. So the minimal polynomial is in fact the full product here. For the converse, we would suppose that this is the minimal polynomial, and we want to show that tau is diagonalizable. We can remove a linear factor from the minimal polynomial. We'll call that m not k of x. This symbol is one of the logical symbols used for negation or not. So I like to use it here. M not k of x reminds us that we're pulling out x minus lambda k from the minimal polynomial. These polynomials are relatively prime. They're not pairwise relatively prime, but all those polynomials together, k ranges from 1 to m, if you take them all together, there's no common factor other than constant. So we can apply Bezo's identity. There are polynomials qk of x for which this linear combination equals 1. And so every vector, little v, can be written in this form. Now some of these terms may be 0. They're not all 0 unless v is 0. So if v is non-zero, then we can look at the non-zero terms. They are eigenvectors, and they're associated with different eigenvalues, because if you apply x minus lambda k to this particular kth term, you can rearrange here and you'll get 0. So the non-zero terms here are eigenvectors, which means that v is a linear combination of eigenvectors. And so the operator module is a direct sum of eigenspaces. This sum is always direct. We proved some time ago that eigenvectors associated with distinct eigenvalues are linearly independent. So this is a direct sum. The issue is whether it equals the whole operator module, and that's what we just proved. And so tau is diagonalizable. So this is quite a theorem. It has quite a lot of parts to it, but it is important. It characterizes the diagonalizable operators. Remember when we, in our initial discussions, we said there were two directions that we could go in looking for canonical forms, and since we couldn't always find diagonal canonical forms, one direction was to restrict attention only to diagonalizable operators. And so this theorem is certainly on point with respect to that question. This is how you characterize diagonalizable operators in a variety of ways, most of which are only have only minor differences. For example, these two since we know this sum is always direct, this will equal the full space if and only if their dimensions add up to the dimension of the full space. So these are almost, they're very similar. Okay. We have seen that the following are similarity invariants. The spectrum of a matrix, we'll talk in matrix language, even if we throw in and we could throw in the geometric multiplicities as well. So the family, the multiset of eigenvalues together with their geometric multiplicities is a similarity invariant. The characteristic polynomial, the minimal polynomial, the determinant, the trace, all of these are similarity invariants. They're constant on the similarity classes. But none of these is complete. None of these characterizes the similarity classes. None of these are systems of distinct representatives, canonical forms for similarity. In fact, all of these together are still not enough information to identify a similarity class. And I wanted to give you an example of that. Here are two matrices of the same size, 7 by 7. All the entries that I didn't put in are zeros. It seemed easier to see what's going on here if I didn't put in all those zeros. These matrices have the same determinant and the same trace, easy to check. Their spectrums, their spectra are both of the spectra are trivial, so they're the same. Characteristic polynomials are the same. The minimal polynomials are the same. This one's easy to check. This is a little matrix multiplication. You just have to check that when you cube these you get 0, but when you square them you do not get 0. These are the eigenspaces for the one and only eigenvalue, 0. They're different eigenspaces, but they have the same dimension. So they have the same geometric, so the the eigenvalue has the same geometric multiplicity, 3. So for these two matrices, this list of data is identical, and yet these matrices are not similar. And I left that for you to show as an exercise. I gave a hint in the exercise set to help you out. So where we stand at this moment is that we have a lot of similarity and variance, but even if we take all of them together, we still don't have a complete similarity and variant. So I guess it should be pretty clear by now that it's not so easy to find a complete similarity invariant. In fact, we won't find one until we reach the chapter on canonical forms, which is a little bit away off yet. But in case you're curious and you can't stand the suspense, I will say a few things about it. I will show you, in very general terms, a complete similarity invariant. We have seen that the multiplicity of a root of the characteristic polynomial, a root that lies in the base field, for an operator is called the algebraic multiplicity of lambda, of the eigenvalue. We will see that the multiplicity, I called it ek, of the eigenvalue lambda k as a root of the minimal polynomial also plays a very significant role. It's a little too early to get into any details on that, but that it shouldn't be surprising. The minimal polynomial is important, and so the multiplicities of its roots ought to be significant in some way. Suffice it to say that, at least in the case where the minimal polynomial splits into linear factors, we can gather the linear factors together based on the eigenvalues. So these lambda 1 through lambda m are distinct. In this case, the prime power factors of the minimal polynomial will lead us to, or will generate, however you want to say it, will lead us to a generally larger sequence of polynomials. And they are generally organized this way. The first row here starts with the prime power factor of the minimal polynomial corresponding to lambda 1, and then we have additional factors that are powers of the same binomial, x minus lambda 1. Traditionally, we arrange the exponents in decreasing order. That's not essential, but that is often done just for simplicity, I guess, or for organization purposes. Then we go to the next prime power factor, x minus lambda 2 to the e2, and that will, in general, spawn additional powers of x minus lambda 2, and so on. So we'll get this huge collection of prime powers of the linear factors of the minimal polynomial. These polynomials are known as the elementary divisors of tau. And as I said, we generally organize the exponents this way. Now this collection may contain duplicates. In a given row, some of these exponents may be the same. None of them are bigger than E1 here, which is the power that comes from the minimal polynomial. So this is in fact a multi-set in general, the elementary divisors. The multi-set of elementary divisors is, at long last, a complete similarity invariant. Now, of course, this is all very general vague discussion now, but I just wanted you to see that this is what it takes to get a complete similarity invariant. So this indicates that we can get one, at least in theory, and it is definitely in theory, because this requires the factorization of the minimal polynomial. And if that's more than a cubic, we're in some trouble, and if it's more than a quintic, we're in big trouble. So this is a theoretical discussion. It also shows us clearly that we didn't, we probably didn't miss anything in looking for a complete similarity invariant. They're not very easy to find. So that's just a look ahead. And we're going to begin the journey towards this goal here. And the first step is going to be to take a closer look at the minimal polynomial and its monic prime factorization. So we're going to factor the minimal polynomial into a product of powers of monic irreducible. Irreducible means prime. Well, shouldn't have said that. Irreducible and prime are equivalent. So you can think of this as the prime factors, powers of prime factors, or powers of irreducible factors. It's the same thing. That's going to be the starting point, starting in the next lecture, for our journey into the structure of linear operators and canonical forms.